Alright, so today I'm going to talk to you about the difference between series and parallel circuits. It's a fairly straightforward concept, but is very important in further circuit analysis, and you're definitely going to need to use it in the future. So I'm going to use some resistors as an example to show the difference between these two types of circuits. So here we have a series connection of resistors, which basically just means you have one resistor connected directly to another, connected to another, dot dot dot, go on. Usually you see this in circuits with some sort of voltage source and perhaps a resistor and then another resistor connected back. So these two would be considered to be in series. In parallel circuit configuration, you have one resistor here, one resistor here, all the way out to another resistor connected like that. Usually you find these in configuration with, let's say, a voltage source, then one resistor, and another resistor here. Usually see R2, R1, something like that. These would be considered to be in parallel. So what's the significance of this? Well, it has a big effect on the current and voltage that goes through these circuit elements. Let's start with the series example. A good way to analyze and assess how these configurations affect the voltage is to find the equivalent resistance. Basically all that means is taking these two resistors and condensing them to a single resistance value that's equivalent to the resistance provided by these two separate resistors. So in series for resistors, it's a fairly straightforward process. Let's say we have our circuit again with R1 and R2, and let's say R1 is 5 ohms and R2 is 2 ohms. R equivalent would be equal to R1 plus R2. So 5 plus 2 is 7 ohms. And this can be extended to be applied in any number of resistors in series. So if you had R1, R2 to R to the N, R equivalent would just be equal to R1 plus R2 dot 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 plus Rn. If I can do R. So in series it's fairly straightforward with resistor elements. In parallel, however, it's a little bit different. You have, say, your voltage source, R1 and R2. Let's just have 2 for instance. Let's extend this out. Let's say you have up to Rn resistors in parallel. The equivalent resistance of these, as seen by this voltage source here, so basically this entire block of resistance, can be written as 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over Rn, however many resistors you have in parallel. So let's have an example to illustrate this concept. Let's say you have a voltage source here, and we just have 2 of these in parallel. So let's call this one R1 and R2. And let's set R1 equal to 3 ohms and R2 equal to 5 ohms. So using this equation that we just established up here, we can say that R equivalent is equal to, well, 1 over R equivalent is equal to 1 over 3 plus 1 over 5. So you can use algebra and essentially solve for the equivalent resistance. An easy way to do the parallel equivalent resistance whenever there's just 2 elements, which is a very common occurrence, I find it best to use a kind of shortcut where you can do R equivalent equals R1 times R2 over R1 plus R2. You're going to see this a lot. That's pretty much what I always end up using in my courses. So in this case, you can find it very simply by saying 5 times 3 over 5 plus 3, which results in a really bad number, but it works, which is 8 over 15. If you were to do it this way, it'll work. If you were to do it this way, it would work the same way. I'll show you that if you'd like. You get 1 over R equivalent equals common denominator 3 over 15 plus, oops, oh, I mixed it up there, but you could do 5 over 15 plus 3 over 15, which means 1 over R equivalent equals 8 over 15. You take the inverse of this and you get 15 over 8, which is the same answer we got here. So it works out to be the same. Now things get a little bit different whenever you deal with circuit elements other than resistors. A common one you're going to come across is called a capacitor. I'm not going to go into too much detail about the theoretical background on capacitors and capacitance, but I'm going to show you the difference between analyzing parallel and series capacitors. Whenever capacitors are in series, like this, it's essentially the opposite case of the resistance. In this case, capacitors in series, the equivalent, say C1, C2, Cn, where n is the number of capacitors hooked up in series. The equivalent capacitance in series is 1 over equivalent capacitance equals 1 over capacitance 1 plus 1 over C2 all the way to 1 over Cn. Similarly, in parallel, I'll write this series. Parallel, say you have same deal, connect them all in parallel, C1, C2, Cn. In parallel, they're just added up. So that's your equivalent capacitance in parallel. And we can do an example just to solidify this concept. Let's say we had voltage, I'll say 1, fiddle right, okay, there we go. Say 1 farad, well, that's huge. Yeah, we'll say 1 farad, 2 farad. Those are kind of unreasonable numbers, but essentially it's the same algebra. It works out to be the same. 1 over C equivalent equals 1 over 1 plus 1 over 2. Or you could use a little, or you could use a little shortcut that I did before, where it's just the multiplication of 1 times 2 over 1 plus 2, so 2 over 3 would be the equivalent. And in parallel you just add the numbers together. So I wanted to get a quick summary here to pull this all together and how you're actually going to use it in circuit analysis. So let's start with a simple example involving resistors. Here's your voltage source, and let's say you have, this is what you'll commonly end up seeing. Let's make these nicer numbers. Let's make it 5 ohms and 10 ohms. And then like that. Let's keep multiples of 5. So in this scenario we want to find, let me switch it, we want to find R equivalent as seen by this voltage source. So a good way to break this down is do multiple steps. You start with your simple series combination, and we know in series these resistors just add together, so 5 plus 10 is 15 ohms. So then it's in more complex circuits, it's nice to kind of redraw it in a secondary step. So you redraw it once you find this result, you can redraw it as 15 ohms. And this 15 ohms just came from these two added together in series. And then that's still in series, in parallel. This 15 ohms that we added up is still in parallel with the other 15 ohms. And then to find the total equivalent resistance, we just add these two in parallel. So using our little shortcut, we can say R equivalent equals 15 times 15 over 15 plus 15, which is 225 over 30, which is probably not a nice number either, but it works out. 7.5 ohms. So this 7.5 ohms, you can basically use it to redraw that entire original circuit here. You can use that value now to redraw this entire circuit in terms of the equivalent resistance as just a voltage source, a single resistor, and 7.5 ohms for the resistance. So you can apply those same concepts for capacitance, except you just use the opposite, essentially, approach. So these are very useful to know and have a good grasp on before you try and use more advanced circuit analysis techniques like Kirchhoff's voltage and current laws.